charged atoms distributed around the face of a clay mineral that's suspended in water. And the notion that they're in thermal motion, like bees around a beehive, so that they're distributed away from the surface of the clay mineral particle. What I'd like to do this morning is to describe some simple theories that don't accurately calculate the distribution of ions. That is, when you compare experiment to calculations, they don't quite agree, but qualitatively they agree very well, which means that we can use the concepts to gain insight into the processes, that is particularly the factors that affect the distribution of ions away from the surface. And as you'll see later, this determines the cohesion of the of clay particles one to another. There have been a number of theories. You have chalk back here?
There should be some over on the side.
Oh, I see. In 1879, Helmholtz came up with a theory that of the distribution of ions around a charged surface that was essentially analogous to a double plate condenser. That is, he had positively charged ions attracted to the negative face of a clay particle, and he assumed that they just laid on the surface so that it provided a condenser with a spacing of something like this. Now, 1879 was some time ago. He was a real early worker, and he just assumed that it was a parallel plate condenser and made computations accordingly. Then Gouy in 1910, and Chapman in 1913, independently, described the distribution as a diffuse layer, as I described to you. That is, positively charged ions distributed away from the face due to the thermal motion of the ions in the surrounding water. So this is, we'll call it parallel plate condenser, electrical condenser, and this is a diffuse double layer. Then in 1924, Stern combined the two. He said that, well, most likely there's a layer of charged atoms adhering to the surface, and then in addition to that there are ions out in solution that are diffuse. So he combined the two, and the reason that concept is important is that the dimensions of the ions assume some importance. In the theory that we'll discuss this morning, which is this one, the ions are assumed to be points, point charges. But if you consider the hydrated size of the ions, they can only get so close. So that there's a portion of the distribution that's fixed by the size of the ion. What I'd like to do now is to describe this diffuse double layer theory in its simplest form. I handed out to you a description of a more complicated solution, as well as a simple solution that I'm going to describe now. And you can read that at your convenience. Well, we can describe, I'll go back to this double layer now, diffuse double layer, and we'll assume that each of these are point charges. We can describe the distance away from it, I'll call it x. That's x is the distance here. And the work necessary to bring a charge from infinity, somewhere way away from it, toward this surface in a one-dimensional sense. In other words, we'll forget about edge effects and so forth, because the clay mineral particle is very platy. I forgot that demonstration I brought. This is a sample of biotite. Just pass it around. It's a big illite particle. Remember, illite's on the order of a couple of microns across, a couple of millionths of a meter. But it looks just like that, and it's mineralogically very similar. So when we talk about a plate, a surface like this, recognize that it's very long compared to its thickness. And we can reasonably well represent the distribution of ions just in terms of their number per cubic centimeter as a function of distance out. Well, we can put number per cubic centimeter here, and you'd expect it to diminish to some level where this is the value. I'll call the number per cubic centimeter n here to some n in the bulk solution. It falls off with distance. Now you can see that if we took an ion from out in the bulk solution and brought it to the surface, that there would be attraction to the surface as it gets closer and closer, so that the work necessary to bring it to the surface is negative, but it would change with distance. And we'll call that work the potential phi. From some long distance away to a point. Let's say to x. So the potential at this distance, now we can draw, instead of number concentration, we can draw x here and this potential, and it falls off in some way. That is out. See, it will go down to 0 out at infinity, won't it? So it'll fall off something like this. And this is 0 here. While I'm talking about potential, there's a potential that is common, you'll see commonly in the literature, called the zeta potential in the literature on clays. And if the potential, we'll call this phi 0, that is right at the surface of the clay, and then there'll be a potential we'll call a zeta potential at some distance x. And the reason that potential appears and is of common concern is that if you put a clay mineral particle with its ions associated with it in a suspension, then put two conducting plates, two platinum plates, let's say, with a potential across them, connect them to a battery. So one's positive and one's negative. The clay mineral particle will migrate to the positive plate. That is, it'll move in this field. And you can calculate the dimensions of the plate and, of course, and the charge of the plate, of the particle, as it moves by its velocity, moving through the fluid, and the temperature, viscosity of the fluid. And it turns out that the potential of the particle is something less than the total potential. It means that there is water and ions that migrate with the surface particle, absorb water on the particle, so that it appears in solution as a larger particle than it actually is. I'm going to spend a lecture talking about water associated with mineral particles later, but for this point, for now, just bear in mind the zeta potential, commonly described potential for the surface of clays, is something less than the potential on the clay mineral surface, at the clay mineral surface. Now, we're assuming these to be point charges, so they come right to zero, and I've drawn this curve right to zero. Actually, they're not. They don't come right to zero. We'll discuss that later too. So we have a potential that is the work necessary to bring an ion to X. And the way I drew this is minus. That is the it actually gets up energy that comes in. And it's the ion is attracted by the negative surface. Now, we said that the distribution of these ions away from the surface results from the thermal agitation. And we can describe that distribution in terms of Boltzmann's equation. Which is that the number at any distance, I'll call it n sub I, is equal to the number I0 that's out at infinity. Let's say at x equals infinity. Times e to the minus, I'll put exponent. Exponent e sub I minus e sub I0 divided by kt. This is Boltzmann's constant. And it's 1.38 times 10 to the minus 16 ergs per degree Kelvin. It's also 1.38 times 10 to the minus 23 joules per degree Kelvin. And T is the absolute temperature. In degrees Kelvin. So this is essentially difference in energy between that at any point. Just X from the surface of the clay mineral divided by the thermal energy, the average thermal energy of the ion. And E0 is the potential energy, of course. We'll let E I0 equals 0 at x equals infinity. That is way out in the solution somewhere. for our description. Then we can write E I have here EI equals V epsilon times phi, where Z is the valence ion of the ion, and it can be plus or minus for negative or positively charged ions. E or epsilon is the electrostatic charge. It's 1.59 times 10 to the minus 19. Cool. Or 4.8 times 10 to the minus 10 ESU, electrostatic units. So we can now write this relationship Ni equals Ni0 e to the power minus Z epsilon phi divided by KT. And remember that both Z and phi potential can be plus or minus. I'll introduce another electrostatic forces. We have the energy of the ions now as a function of the valence and potential. What it says really is that the energy greater than this energy is equal to the total number times the e to the power of this relationship. So Ni is the...
These are the bulk fluid values of N where Ni is 0. Is that what you're saying? Yeah, out in the... Well, the assumption in that equation is that EI0 is equal to 0. In other words, we're at some x equals infinity. Is that right?
EI0, yes, is equal to 0.
So we're way out in the bulk.
Way out at x equals infinity. Poisson derived an equation, and I won't take time to derive this morning, that says that the change in potential, or the second derivative of potential with respect to distance, is equal to minus 4 pi rho over d. I want to make sure I've defined all of the terms so far. I think so. Okay. D is a dielectric constant. And it's 80 for water. It's about 30 for alcohol. And about 2 for benzene. It's the highest for water. It's higher for water than any other known liquid. Just a point of interest. Water is really a peculiar substance, as you'll see more and more. It's the ratio of, well, if you take an electric condenser and measure its capacity, you remember from physics of  measure its capacity in a vacuum, and then measure its capacity with water between it, what you'll find is that the capacity is 80 times as high with water as it is in a vacuum. So it's the ratio of those two things. It's also the conductivity for lines of force, if you like it, to think of it in terms of electrostatic forces. Now let's see, I can illustrate that, I think, by saying, pointing out that the force between 2 point charges is equal to the charge on one Q1 times Q2 divided by R squared, the distance between them, times the dielectric constant. So 1 over d, the force is proportional to 1 over d. Rho here is the number of charges per cubic centimeter of point charges per cubic centimeter of solution. And rho is equal to the sum of, I'll bring the ESU value out. It's the sum of all of these ions Zi times Ni.
What are the units on D?
What's that?
What are the units for the dielectric constant?
Units? See, it would be, let's see if we can figure it out from this. I think it's dimensionless. Yeah. We have charge squared divided by d r squared, and the force, let's say, is in dynes, equal number of charges. What's the quantity of charge? Q, isn't it? It's the units are number. Aren't they just numbers? Times E. I think we're going to run aground. I'll tell you. I'll double check on that and bring it to you next hour. I think it's dimensionless.
The ratio of charges should be
It's a ratio of capacity. It should be different.
Yeah, it should be dimensionless. So, but I'll verify that for sure.
Water to vacuum.
Yeah, if you take the capacitance of a parallel plate condenser in a vacuum and the parallel plate condenser in water, pure water with no atoms or ions in it, then the dielectric constant is the ratio of the capacitances. So that would be dimensionless. Dimensionless, yeah. So we have an expression for n sub I over at the other end of the board there. So we can combine the Poisson equation and the Boltzmann equation to give the second derivative of the potential with respect to x. 4 pi epsilon over d times the sum of the I n I0 exponent minus the epsilon phi over kt. And this is called the Poisson-Boltzmann equation. We can consider a special case now to bring out the points that I'm seeking here. Single compound, say calcium carbonate or calcium hydroxide or calcium sulfate, let's say. So that we have calcium ions and sulfate ions in solution. This greatly simplifies it because we don't have to worry about the difference in the valence of the charges. And for this simple case, we can write d squared phi with respect to x squared is equal to minus 8. I won't go through all the arithmetic. Pi n0 I0 exponent. Well, let's leave it z epsilon divided by d times the hyperbolic sine of z epsilon phi divided by kt. And for phi 0 low, to further simplify it, we can write the solution is phi equals phi 0, phi I, I'll call it phi I0, e to the minus kx, oops, capital Kx, where k is equal to 8 pi ni0 z epsilon squared z squared over k t d. K squared is equal to this. So this must, to make this dimension, this must be dimensionless. So we can write this is equal to phi I0 e to the minus x over 1 over k. This 1 over k is a distance that normalizes x for our solution, right? And 1 over k is approximately the distance to the center of gravity of an ion cloud. So you often see the term 1 over k is the thickness of the double layer. It's a distance to the center of gravity of the double layer, with this assumption of point charges and 1 over k squared. 1 over k is the distance, so we have k squared here. So k, 1 over k then, is equal to the square root of dkt divided by 8 pi ni0 epsilon squared z squared. And this is really what spent this morning's half hour getting to.
Question, when you say that's equal to the distance to the center of gravity, are you talking about the center of mass, or are you talking, or is...
Center of number concentration. Remember we said the number concentration as a function of x. Ni fell off something like this. So it's the center of gravity of this, some distance out like that.
I was just thinking if
So-
you had a mixed solution with different ions in there or something.
This is the simplest case. A single ion could be sodium or potassium, and I want to discuss that. And because the solution is an exponential, it falls off exponentially, this goes on mathematically to infinity, goes on some great distance. So you can't really define any dimension, length of it, I should say, specifically, other than as a center of gravity or some fraction of the total. No. Now, it's this distance that affects the cohesion. So I want to talk about what this distance 1 over k, what affects this distance 1 over k. Well, first of all, you can see that the concentration of ions out in the bulk solution, this is Ni0, has a significant effect. The greater the concentration, the shorter this distance. It's in the denominator, right? It goes roughly with the square root of the distance. The greater the charge on the ion, the shorter the distance. Okay? And in fact, it's inversely proportional to the charge on the ion, on the surface of the ion. So that what happens if we put in calcium instead of sodium? Let's say this is that they were all sodium ions, and we replaced it with calcium ions, then the calcium distribution would look something like this. I'll draw that solid line. So what you'll read is that increasing the valence collapses, that means it makes it closer, the thickness of the double layer of the layer of absorbed ion. So these are very important factors as far as the distribution of ions is concerned. The effective temperature is more complicated. The reason it is that as the temperature rises, this is absolute temperature, as the temperature rises over ranges of ordinary temperatures in estuaries, the dielectric constant falls, so that the two kind of compensate each other. Actually, as temperature rises, the dielectric constant goes down a little bit faster than the temperature. So the two things we'll really be concerned with are the concentration of ions in the bulk solution and the valence of the ions. Now there are several things that aren't included in our description here. I pointed out earlier that this does not accurately represent what you find experimentally, but it qualitatively does. That is, the points I just made are true. It changes roughly inversely with the charge on the ions and inversely with the square root of the concentration of the ion. There are several factors that aren't included in this theory that affect the distribution of ions too, and I want to point those out before we get too far away from it. First of all, as I mentioned earlier, Stern said that ions can only get so close because the ions are hydrated. They're fairly large, and they can't get closer than their dimension. The center of the ion can't. So the actual distribution of ions, I'll put the number concentration here, must look something like this. That is, there's a layer of hydrated ions next to the surface, that if we drew the potential from this point on, the potential must just be some kind of a straight line and then curve below that point. Now, the position of the zeta potential doesn't seem to coincide with that, but who knows? It may be that they stack up a little bit on top of there. Still, the ions must be in thermal motion because they can be displaced by putting in high concentrations of other ions or ions of higher valence. Another factor that's important is the pH, especially for kaolinite. There's a reaction we can write AlOH 3 in water is in some kind of an equilibrium with ALO minus and Al and H2O. Oh, I'm sorry, and H. Plus. So you can drive this reaction back and forth on the surface of kaolinite. Remember, the open bottom side of kaolinite is aluminum hydroxide, essentially the earth. So changing the pH will change the effective charge on the surface of the clay mineral particle. In fact, using the electrophoresis, that is measurement of the velocity of the particles in an electric field, now I mentioned earlier, you can adjust the pH higher or lower and find some pH where the particles don't move at all. That is, you can just compensate their negative charge by changing the amount of aluminum on the surface. That's called the point at which there's no motion is called the isoelectric point. You'll find that in the literature. Another factor that's not included in our theory has to do with edge charges. The edges are typically positively charged while the faces are negatively charged. And anions are absorbed on the negative face. They can make the mineral particle appear more negative if there's a lot of particles there. I think those are the major factors. Okay, so where we've arrived is that we can change the distribution of ions in the neighborhood of the mineral particle by changing the valence of the ions that are there, that is replacing calcium with sodium, or by changing the concentration of ions that are there. There's one other factor that isn't accounted in this, that isn't apparent immediately, but that is that the potential, I'd better redraw the it's an important point, I think. By whatever means we draw this potential curve here, one thing that's really important is that phi 0 here is fixed by the mineral surface. Can be modified by pH, as I indicated earlier, but essentially it's determined by the substitution of ion in the mineral, by the charges on the mineral surface. So this, while this can be changed with pH to some extent, it's otherwise fixed by the mineral kind. Montmorillonite has a higher surface potential than does illite, and illite higher than kaolinite and so forth. But this limitation on the potential limits the number of atoms, number of charges that can be attracted And of course, the size of the ion determines the number of atoms, number of ions that can be laid on the surface, stern layer. You can only get so many per square centimeter on there. Keep this in mind as we go on. Okay, with that, kind of a description now, let's start talking about cohesion. While I'm erasing the board, I'll just re-emphasize. We can change the distribution of ions near the surface of a clay particle by changing the concentration in the bulk solution or by changing the kind of ions. And of course, the size depends on the mineral. The actual distribution depends on the mineral kind. Temperature also has an effect, but I'll discuss that further. Well, now let's begin to talk about cohesion. Recall I described van der Waals forces. Remember I said between points, the attractive force is proportional to 1 over the distance to the 7th power. Very, very weak force. Between parallel planes, of crystal or mineral atoms, the force is proportional to 1 over the distance cubed, because the one atom is attracted by many atoms in the other. Recall I described this attraction as due to the instantaneous dipole formed by the motion of the nucleus within the cloud of electrons. And that I pointed out that it's omnidirectional, that is in all directions, operates in all directions, and that it's universal. That is, all matter made of atoms, anyway, exhibits this property. So we have van der Waals attractions, very short range forces. There is some theory comparable to the theory I just described for distribution of ions for van der Waals attraction. It's complex and it doesn't give us much more insight than I can just describe qualitatively, so that's what I'm going to do. If we drew a graph where this is this separation of clay particles, and we'll consider for simplicity here 2 clay particles, each with their negative charges and their ions distributed around them. Let's just consider them parallel to one another to start with ions in here. And I'll draw the distribution of ions, of cations, like this, as you bring them together this way, as they move in this direction towards each other. The ions, clouds overlap, and the anions might look something like this. And this is in suspension, suspended in water, and in salts. Ion. So that if we have the 2 coming together toward each other, we can describe, first of all, their attractive forces due to van der Waals force. And let's say this is attraction. And this is repulsion. Now let's, in your mind, bring these 2 clay mineral particles toward each other. What will happen is that the ion clouds will merge. That is, the ion clouds associated with one particle will merge with the ions cloud associated with another particle. And like charges repel, right? So that as they get closer and closer together, because the ions are distributed away from the surface, as we described earlier, there'll be more and more repulsive force, right? So we can draw qualitatively, at least, a distribution of repulsive force that might look something like that. I guess it has to go down to 0 eventually. At the same time, these van der Waals forces that I described are becoming increasingly effective because of the proximity of the particles. As they get closer and closer together, the van der Waals forces get stronger and stronger. So we can describe that as something that looks like this. And this is electrostatic. Yeah. Repulsion. Due to the ion clouds. So the sum of these forces then would look something like that. In other words, with the distribution I showed here, as the ions got closer together, the net, the resultant, is repulsion. So the particles won't be attracted to each other at all. In fact, they'll be repelled. And under this scenario, this set of conditions, the particles are said to be dispersed. That is, whenever one approaches another, it's pushed away, so the particles stay separate. You follow me? This is the case in rivers. The wash load is typically dispersed. That is, the clay minerals in the wash load, typically dispersed because the ions, when they're brought together by hydraulic or other forces, are pushed apart again, and they just stay separate from each other. Because they're very small, they settle very slowly, and the result is they just stay suspended in the water, and their transport is just with the water. Okay. Now, we spent all morning describing how this distribution can change. If we change the valence of the ions, for example, let's say this is sodium at some concentration. If we change it to calcium, then you'd expect this curve to collapse. That is, to be pressed against the surface of clay mineral. So that for calcium, then, it might look something like this. Or magnesium or something like that. Now the sum of these can, well, the way I have it, I didn't quite make it attractive enough, did I? Better do that better. Something like this. The sum of these now is attractive. So the particles, as they're brought together, they don't see any kind of a hump or resistance to motion. They can simply get closer and closer, and as they get closer, they're attracted more and more strongly. And then finally, when they touch each other, the van der Waals forces is by far the dominant force, and they just stay stuck to each other. Then the particles are cohere, and that's cohesion. Okay, so we have a situation where changing the valence of the ions, assuming that the equilibrium is established and so on, changing the valence of the ions changes the distribution of charges and makes them cohesive. In rivers that pass through limestone formations, calcium carbonate, magnesium carbonate, you often find that there is enough calcium in the water to make the particles cohesive, weakly cohesive, enough so that when they flow into an impoundment, they combine and settle out behind a dam. And there are some dams that are filling up with mud because of this process. we talked about concentration of ions, and as pointed out earlier, if you increase the concentration of ions, even sodium ions, it will depress the thickness of the double layer. And if you raise it far enough, then it will depress it to the point where the sum of the two forces is attractive. So just by increasing the concentration of sodium ion high enough, you can depress the double layer sufficiently to make the particles cohere. Now that's exacerbated or made more effective, I should say, by the fact that the charge on the surface clay mineral is limited, I pointed out earlier, so that when we have if we raise the concentration of ions we can also describe this as concentration. I'll put this as Ni. Since the maximum number of ions that can be attracted to the surface because of space and because of the limited number of charges on the surface is fixed, if we raise the concentration out here in the bulk solution, let's say we raise it up to this concentration out in the bulk solution, then the concentration is going to look like this, or something like this. In other words, there won't be any change in the concentration until the particles are quite close to one another. So in effect, you've compressed the double layer relative to the concentration in the bulk solution. And the atoms can come closer, or I'm sorry, the clay mineral particles can come closer and closer before they even notice there's much different. Because everywhere in the solution the concentration's high. Do you follow me? So they can get quite close before and concentration increased in the particle begins to overlap with one another. Do you follow me?
I'm not sure I'm following exactly. This curve that you're doing in the second panel there, are those clay particles with attached ions?
This is distance apart between clay particles on this axis here, and the clay particles are being brought together this way.
Right. This distribution here, though, was for the ions in solution.
This is ions in solution out here, and then the concentration gets higher as you get closer and closer to the particle because of the charge.
Okay.
But because this is limited, as you raise the concentration in the bulk solution, there's not much change until a point close to the particle surface is reached.
I followed you on that. And
So in this case, there's the repulsion force is depressed now against the surface of the clay mineral to a short distance from the clay surface.
but those curves refer to the ions in solution.
No, these are forces: repulsive force and attractive force. These curves.
The forces on the ions in solution.
The forces on the clay particles. Let me repeat that because you have to have this clearly in mind. Let's in our minds do an experiment. We'll take two clay particles, make them parallel to each other for reasons I'll explain later. Make them parallel to each other and gradually bring them together. Each has a cloud of ions swarming around it, and the ions are predominantly positively charged ions. Okay? And as they get closer and closer to one another, the clouds begin to merge, right? And as they merge, the like charges tend to repel. So that as you get closer and closer, the repulsive forces grow more and more. And this is a repulsive force here. That's what this curve is here. If the clouds are compressed, that is, if they're compressed against the surface of the clay particle, they can obviously get closer together before they feel that repulsive force. And that's this scenario. The van der Waals attraction is fixed by the orientation of the particles and the distance apart. The orientation of the clay mineral particles and the distance apart. So I just drew one curve for that. So as long as that orientation is held, then we can sum up the repulsive and attractive forces, and when the sum is attractive, the particles are cohesive, and when the sum is repulsive, the particles are dispersed. Now, I mentioned, I arranged this nice parallel orientation to simplify the thing. You can see that if the particles are at some angle to one another, that there's more attraction at this end than there is at this end. And while the curves will qualitatively be the same, they'll be displaced. They'll be slightly different from each other. That's also affected by the fact that the edges are positively charged, so that if they're brought together like this, the edge itself will be attracted to the other side, and that will add to the attraction, tend to make them more cohesive. In fact, if particles with high charge densities like montmorillonite are suspended in snow water, in virtually distilled water, the ion clouds have a negligible effect, and this positive edge is attracted to the negative face, and the structure is what we call a card house structure. There are reservoirs in Montana that are filled up with clay that has this card house structure. The density is very close to that of water, practically all open space like this. So not much clay occupies a huge volume of the reservoir. It's a interesting phenomenon. Now, in general, increasing the temperature tends to increase this distribution slightly. It causes greater thermal motion of the particles, and generally the strength of the cohesion diminishes with increasing temperature. That's not shown as well by the point theory that I described as it might be, but I'll give you some information on that before too long. Now, what about mixtures of ions? We started out talking about the effect of just calcium, a calcium ion, for example, or a sodium ion, a pure solution. What about mixtures of ions? We have to get off into pretty much empiricism when we talk about mixtures of ions, and I'll give you some useful descriptions of ions, of mixtures of ions. The ions in natural waters that we'll be concerned with, the dominant ions, are sodium, calcium, and magnesium. In seawater and in river waters too, these are the ions that have the greatest effect. The others are all relatively minor in natural waters. There is a term called ESP, which is exchangeable sodium percentage. Which is the exchangeable sodium ion divided by the cation exchange capacity. That is the fraction of the surface that's covered by the fraction of the adsorption sites or sorption sites that is covered with sodium ion. And these are in milling equivalents for 100 grams dry soil, dry particles. Another one called the sodium adsorption ratio or SAR is based on equilibrium concepts of sorbed and dissolved ions. Let me describe the origin of that. There's an equation called Gapon's equation. Of chemical equilibrium. And he said that let's consider sodium ion adsorbed on the clay, and I'll call the clay X. Plus calcium ion plus magnesium ion bumped together, both divalent. 1/2, should be 1/2. This is in equilibrium with calcium plus magnesium ion adsorbed on clay plus sodium ion. He simply says that calcium and magnesium and adsorbed on the clay is in equilibrium with that all of this is in equilibrium. So we can write an equilibrium constant, K, is equal to the product of the reaction, which is Ca Mg to the 1/2 power. Oh, wait a minute, I have this on the X particle here. Times Na concentration, ion, divided by the product of the reactants, NaX concentration, times Ca plus Mg to the 1/2 power. So this is our equilibrium constant for this reaction. Now we can rearrange this algebraically to give K times Na adsorbed on the clay, NaX concentration, divided by C calcium plus magnesium 1/2 adsorbed on the clay is equal to Na plus concentration in solution divided by the calcium plus magnesium ion concentration to 1/2. So what we say is that the ratio of the sodium ion concentration, this is in moles per liter if you like, sodium ion concentration in solution to the calcium and magnesium ion concentration in solution is proportional to their ratio on the clay. Now the reason for going through this exercise is that this is much more difficult to measure than this. You can take the water now with ion selective membrane electrodes, if you like. You can just measure these directly, or with any of the commercial things. Whereas to determine these, it's necessary to displace them with say ammonia, normal neutral ammonium chloride, wash them out, put ammonium on in place of the sodium and calcium and magnesium, and then determine the amount in the washed out solution. So the cost of measuring this is about 1/10 of the cost of measuring this. And this now is called the sodium adsorption ratio. Now, there is a direct relation for a given clay between the SAR and the ESP, as you might expect. Richards demonstrated that, and I can give you a reference in just a minute. Okay, with all of these ways now that we have of describing the solution that the particle's in and its cohesion, did anyone not get one of these? I passed out to you some measured boundaries between cohesion and dispersion for different clays. Look at the one in figure 1. This is for kaolinite, the least reactive of the clay particles. And the solid curves there are boundaries between dispersion and cohesion. It says aggregation, but they were measured by determining whether they'd aggregate or not. That's how we determine these boundaries. And you can see that the abscissa is total cation concentration in milliequivalents per liter. This is in moles per liter, but we can express this in milliequivalents per liter as Na plus concentration divided by calcium plus magnesium divided by 2, the 1/2 power. So that's cation concentration in milliequivalents per liter. Total concentration. Remember I said if you raise the concentration high enough, even if it's a monovalent ion, you'll depress the effective double layer. The ordinate is the sodium adsorption ratio. Okay? So that we have, take the right curve, the one with the circles on it. On the right of that curve, the particles are cohesive. So at very low concentrations, the sodium adsorption ratio can be something like 3, it looks like there, and they'll still be cohesive. But if you raise the concentration any higher, if you raise the sodium adsorption ratio any higher, then the particles will be dispersed. You follow me? So these are boundaries. Now the different curves are for different pHs. So it's a family of boundary curves, if you like, for the different pHs. The next page figures.
What is the dotted line stand for?
That's for seawater. That's seawater pH. You anticipated my. In the second one, we have it for illite, which is the hydrous mica, remember? And notice that the curves right now are spread out. It's a more reactive material, more reactive clay surface. And the particles are cohesive. It takes a higher cation concentration for a given sodium adsorption ratio for the particles to become cohesive. So the activity of the surface, that is the amount of negative charge on the surface, strongly determines this. Now if you look at the next one, montmorillonite, you see that the trend is greatly exaggerated. that it takes a much higher concentration to make the particles aggregate. Now, as you pointed out, the dashed line is for the pH of seawater, and we'll be particularly concerned with seawater aggregation. The sodium absorption ratio changes with the square root of the calcium and magnesium concentration and with the first power of sodium concentration. So if you just change the concentration of seawater, that is the mixture of seawater and fresh water, so that the concentration of salts change, the sodium absorption ratio changes with the concentration. And this next curve shows the sodium absorption ratio as a function of sea salt concentration in milliequivalents per liter. And you can see that changes. So that complicates all those other curves that we had there. Now, if you look on the next page, it gives the milliequivalents per liter in seawater. And then, the last page gives table 4, gives the total cation concentration in milliequivalents per liter for seawater, at which the particles become cohesive. And see, for kaolinite, about 1 part per thousand. Seawater is 33 or 34 parts per thousand salts. So at about 1 part per thousand, the particles become cohesive. So it takes very little seawater. 1 part per thousand is 1,000 milligrams per liter. You know, that's just above the drinking water standards. It takes very little seawater to make kaolinite cohesive, and that's because it has small surface charge, and they're easily the double layers easily compressed there. Now, if you look at illite, it's about 2. Well, let's say 1.1 grams per liter, or parts per thousand. And for montmorillonite, it's about 2.4. It's more reactive, so it takes more salts to compress the double layer.
I have a question. I wasn't following your. You've got sodium absorption ratio expressed in 2 manners here, and I didn't quite understand the transition between
This
the
one?
top and the bottom.
This is in milliequivalents per liter. So if you express the calcium and magnesium in milliequivalents per liter, that's half the size.
Moles.
And this is in moles per liter. Concentration, and this is in milliequivalents per liter. Okay, we covered a lot of ground today, and some of it was a little bit sketchy just because of time constraints. I invite you to read that chapter that I passed out to you, and I think you'll find that it gives you considerable insight into these processes that I described today. We won't be doing any computations. I'm not going to give you homework to do computations. I don't think that is a computation of charge distribution. I don't think that's too useful, because the particles in typical estuaries, for example, it's a mixture of particles and a mixture of ions. And we have to resort to empirical curves like this kind of a curve for those. One thing I should mention before we get away today, because it also fits into this picture. Particles have irregular edges. You know, their shape is platy, but otherwise it's quite irregular, as you saw in those electron micrographs. And that also affects their cohesion. That is, if they have a rough edge, then they can only get the tips of the edges is all that can touch the particles. So the orientation, the shape, and the kind of minerals all affect the cohesion. We'll discuss this as we go along, because it keeps cropping up again and again. The basic ideas that I want you to go home with are that we can change the repulsive force by changing the ions and the temperature, the kind of ions, concentration of ions, and the temperature. The attractive forces are fixed by the minerals' the minerals, particularly the shape and the orientation of the mineral relative to one another. Just keep those in mind, and today will have been a success. I'll see you all on Thursday.
I have one other question. If I'm understanding this right, is this curve, the dotted line talks about seawater pH and the expression aggregation of one.
These are boundary curves. On this side of the curve, they cohere, and on this side, they are dispersed. They repel. So,
The dotted line.
no, of each line.
Oh, I
And
see.
this line is for a pH of